Hello everyone, this is Professor Liang. I'm sorry that I cannot be present at the lecture hall today to give you um, the class, but this is a last minute scheduling conflict, and I'm using this video capturing capability provided by Yukon to give this presentation online, and you will be able to rewind and rewatch the videos. This is another way that may be beneficial to the learning process as well. So just a quick recap. The last time we have started chapter 2, and we mentioned the focus will be linear time invariant system, and for this type of system we're interested in, well, given a input signal f of t and knowing the initial status of the system, initial conditions, how can we find or know the output signal y of t? How does the output signal change over time? What is the behavior property and so on? And since we're talking about linear system, we mentioned about the superposition property, and in this case the total response, this y of t, the total output signal, can be decomposed into two parts. One is called the zero input response, and the other is the zero state response. So the zero input response is only caused by the initial conditions. So input equal to f of t equal to 0. And the zero state is caused by the external input f of t only, assuming all initial conditions are equal to 0. And there are some notations. The differential equation we're talking about, notation D represented the differentiation operator. And we have introduced the Q of D, P of D, the polynomials, sort of, to represent the bunch of differentiation operators. And then to solve for the zero input response, which is simpler compared to zero state, we make an assumption that the zero input response will look like an exponential signal. But of course, in this exponential signal, there are two things you need to determine. One is this coefficient c, and the other is the exponent lambda. The two things we need to consider. And the first thing we did is find out the conditions that this lambda must satisfy. And this is carried out in this derivation shown on the screen. And what we have discovered is that these lambdas cannot be arbitrarily or randomly selected. These lambda must satisfy the characteristic polynomial, and this q of lambda equal to 0. And since this is the nth order polynomial or nth order equation, characteristic equation, we know there will be a total of n roots, lambda 1 up to lambda n. And each one of them will correspond to a characteristic mode, e to the lambda it. So lambda 1t, e to the lambda 2t, up to e to the lambda nt. And in general, the zero input response would take this particular form. And of course, these c's are constants that yet to be determined. The lambdas are calculated directly based on the characteristic equation. And at the end, we mentioned, well, if you want to solve for this n unknowns, meaning the c1, c2 up to cn coefficients, we need, of course, n equations, n independent equations from your linear algebra class or algebra class. And this is carried out by plugging in the initial condition. For instance, I give two examples. The output signal or the response at 0, that's your initial condition, right? So, and for all the exponential signals, if we plug in t equal to 0 right here, we'll quickly find out e to the 0 will be 1. So at the initial condition right here, we're looking at c1 times 1, c2 times 1, plus so on up to cn times 1. And for the second case, when we look at the first derivative, okay, that means I take the derivative of each one of these terms. This is y of t, so this is dy dt. And for the first term, lambda 1 will be pulled in front, so it'll be lambda 1 c1 e to the lambda 1 t. But since t, again, at the initial point is 0, so when you plug in t with 0, again you have just lambda 1 c1, lambda 2 c2. And the lambdas you have calculated earlier. You have two equations, and you can just carry on and plug in the initial conditions for all the derivative terms that we have mentioned here. So here you can see these are the initial conditions. Okay. Y, the first derivative, up to the n minus 1th order derivative. These are the usual initial conditions we use in order to find these C coefficients. Okay, so this is what we have discussed. Now, one thing to mention is that these things strictly speaking apply to the case where all lambda i's, so all lambdas above, are distinct. Meaning you cannot have repeated roots. They can be real, they can be imaginary, they can be complex, but they cannot be repeated. And of course, there will be cases where the roots are repeated, but then we'll discuss what may vary on top of that. But let's first look at the case where all lambdas are distinct, and we'll illustrate this solution process through an example. And in the homework that you'll be working on this week, you'll have the chance to practice this particular procedure. So let's start by doing an example. An example will be like this. This is the one I took from the textbook, so just to illustrate the process. And we're looking at a second order differential equation. And I want to write down this formula. Apparently, what's the actual one? So this is the example I usually give. Plus 2y of t equal to, let's say, just 3 times f of t. And let's say I have initial condition y at 0 equal to 1, and dy dt, and again t equal to 0 minus, this is right before the input is applied, this is equal to 2. And let's say I want to know what is the 0 input response. And when you have this, try to match the specific form of this differential equation with the general form of the differential equation we have above, right here, where we have n's of an minus 1, a1, a0, bn, b1, and 0, b0, and so on. And mapping this won't be too challenging once you understand this, right? For instance, in this case, we can say n is equal to 2, since the second order derivative on the left hand side, and you have a1 equal to 3, a0 equal to 2. On the right hand side, n will be 0 since you don't have any derivative terms, and you have only b0 on the right hand side. Okay, so a1 corresponds to the coefficients of the first derivative, a0 corresponds to the coefficient in front of just the alpha segment itself, and b0 corresponds to the coefficient with respect to the coefficients of the input segment itself. And you can again go back to the general form and just check, well, a minus 1 corresponds to a minus 1, a1 corresponds to dy dt, a0 corresponds to y, b0 corresponds to f, and so on. Okay? And you can say all the higher order terms or the coefficients there are basically zeros. Good. So we have this now. And in order to proceed, the first step you want to do is to find the characteristic equation. That's how you find all the lambdas. Okay? And for this one, it's simple. It's going to be lambda squared plus 3 lambda plus 2. And the way to do this is, the second derivative will become lambda squared, first derivative becomes lambda, and the alpha signal itself in the differential equation becomes the constant. And all the coefficients come from the coefficients in the original differential equation. Okay, so when you have this, second step, find the characteristic roots, meaning solve the above equation. And solving this will be easy using calculator, by observation, by hand. You can find the two roots are lambda 1 and lambda 2. In the third step, what you want to do, since now all roots are distinct, so these are distinct roots. Quadratic equation have two roots, both of them are different. You don't have to worry about the repeated roots in this case. And this is where the zero input response y of t in this case will be equal to c1 times e to the negative t, since this is negative 1t, plus c2 times e to the negative 2t. So this is lambda 2t. And the only thing that left to be done is the c1 and c2. So the next step is you plug in initial condition. So plug in initial condition. So this is zero input response, no external input f. Everything you need to worry about will be how the initial condition will generate a response. And we did this, so y of 0 is 1. So if you want to do this, it would be c1 times e to the negative 0 plus c2, or negative 1 times 0, c2 times e to the negative 2 times 0. And apparently e to the 0 will be 0, so c1 plus c2. And from the initial condition up here, we know it's going to be equal to 1. So this one will come to affect this. And the next is the other differential equation. You have c1, c2, two unknowns. So dy dt at t equal to 0 minus. And if you take the derivative of this and this, what you have is negative c1 e to the negative t plus negative 2 times c2 e to the negative 2t. This is the derivative, and we're going to evaluate this derivative at t equal to 0 again, or 0 minus. So we plug in 0 to the t's, you will have negative c1 minus 2c2 equal to 2. And this 2 will come to play in this equation. So when I utilize the two initial conditions, write down the relationship of this coefficient c1, c2. Next thing you need to do is solve this equation. Okay? So if how I did this, you'll find out c1 equal to 4 and c2 equal to negative 3. And again, solving this simple bivariable equation should be a technique that you have already learned from your high school algebra. So I won't repeat it or go into details, but make sure you can solve this correctly. A common mistake I see in homework or exam is that you're not able to do this correctly. Okay. So what this means is that once we solve for c1, c2 in lambda 1 and lambda 2, that will be the last step. The last step is to summarize what you have calculated so that you will know that the zero input response of the system described by the differential equation above, and under the given initial condition, the zero input response is equal to 4 times e to the negative t, that's c1 right here, plus sorry, minus space minus 3 e to the lambda 2t. And usually what I would like to do is I will point it out, well, this is for t non-negative, right? This is after the initial condition, so apparently the t has to be at least greater than or equal to 0. Another way to express this is, since we have the step signal, the unit step signal, you can say, well, it's possible to rewrite this or express this as the multiplication with the unit step signal. Like to turn it on at t is equal to 0, so that means that's how the initial condition will be able to generate or lead to this response, 4 e to the negative t minus 3 times e to the negative 2t. Okay, so this is the first example to illustrate how we can calculate the zero input response of a simple differential equation described linear time invariant system to find the zero input response. Okay, the procedure will be identify your characteristic equation based on differential equation, solve for the characteristic roots, write down the basic form of your zero input response. Basically is a combination of your characteristic modes. Then plug in the initial condition to solve the C1, C2, or Cn coefficients for each characteristic mode, and eventually just put everything together to summarize your result. Okay, so this is the end of the first video clip. In the next video clip, we'll discuss two other scenarios. What if we have repeated roots? What if the roots are not real, meaning in this case we have -1, -2 as the lambdas? What if we have complex roots? How are the calculations differ from this case? And we'll see them in the next video. Thank you.